So hello dear students, this lecture is for final year students, electrical final year. Subject name is electric power quality, subject code is ETEE432. So this subject is for final year students, right? And this SAG is unit number 3 topic, right? SAG is unit 3 topic. So here let me discuss about the SAG. So this SAG is not like the transmission line SAGs. There the topic is different, but here we are discussing this SAG related to electrical power systems, electrical power quality. This SAG means dips in the voltage supply basically. So SAG is a decrease in voltage or current between 0.1 and 0.9 per unit at a power frequency is 50 Hz for a duration from 0.5 cycle to 1 minute. If this duration exceeds 1 minute, then this is interruption, right? So 1 cycle for 50 Hz power frequency is equal to 20 millisecond. Time period is 1 by frequency, so 1 by 50 becomes 20 millisecond. So 0.5 cycle means it is 10 millisecond. So 10 millisecond to 1 minute, right? So what is a SAG? It is a decrease in voltage or current. Let me tell you, this is root mean square RMS value between 0.1 and 0.9 per unit. 1 per unit means this is rated. 1 per unit is rated, but here it is 0.1 and 0.9 per unit at power frequency for duration 0.5 cycle to 1 minute, right? So causes of voltage sag, see here I have drawn this characteristic. On this axis I have plotted a voltage, per unit voltage. This axis is cycles, time period, right? So you see between this time period 0.05 cycle and 0.10 cycle, you can see a momentary voltage dip here, right? Voltage dip you can see. So this voltage dip, that means a decrease, a small momentary fall in voltage. This sag, this is called as sag, right? At this instant and at this instant, right? So voltage sag caused by a single line to ground fault. It can be caused by the single line to ground fault. It is here it is shown the RMS waveform for voltage sag event, right? This voltage sag waveform, right? So effect of the large induction motor starting. See, when a large rating induction motor or high rating induction motor is started, you can see this kind of voltage sag, right? Momentary voltage dip you can see. What is the reason of that? The reason is that induction motor, when it is started, it draws around 6 to 10 times of its full load current. Its magnetizing current is as high as much 6 to 10 times of its full load current during the time of starting. So that means a reactive power demand at the time of starting is very, very high, right? In terms of magnetizing current, it is 6 to 10 times, right? In some literature it is written as 6 to 7 times, right? But let us consider 6 to 10 times of its full load current. And this momentary voltage dip is due to this reason. So due to the heavy demand of the reactive power at the time of starting of high rating induction motor, you can see a momentary voltage dip, and that momentary voltage dip is nothing but the sag, sag, right? So here see sag duration. So sag durations are subdivided into 3 categories, 3 broad categories. See here, from 0.5 cycle to 30 cycle, it is known as instantaneous. 0.5 cycle means 10 millisecond. 10 millisecond to 30 cycle means 600 millisecond, right? So 10 millisecond to 600 millisecond, it is instantaneous, and 600 millisecond to 3 second, it is momentary. That means 30 cycle to 3 second, it is momentary, and 3 second to 1 minute, it is temporary, right? Now what are the swells? Next is swells. A swell is defined as increase between 1.1 and 1.8 per unit in RMS voltage, root mean square voltage or current at the power frequency for the duration from 0.5 cycle to 1 minute, right? Swells are characterized by their magnitude, right? RMS value and duration. So sag means a dip, momentary dip, but swell means it is just opposite to sag, right? That means 1 per unit is the rated value, it is above that, that means 1.1 and 1.8, right? So this is known as swell, right? Swell. What is the meaning of power frequency? Power frequency means 50 hertz. What is the frequency in our country India? Frequency is 50 hertz, right? So at this power frequency, you can see above the rated value, above 1 per unit, this is swell, means it is a voltage between 1.1 and 1.8 per unit. That is a root mean square value, right? From duration from 0.5 cycle to 1 minute, right? Now see here, causes of voltage swell. What are the causes? See here, due to, number one, due to the faults in system, second, due to the energization of the large capacitor banks, right? You know why do we use capacitor banks? Capacitor banks are being used to inject the reactive power into the system, right? So whenever there is energization of large capacitor bank, you can see this voltage swell. That means I can, in loose terms, I can call this as a voltage boost, right? Swell. Second, next reason is switching of large loads, right? So these three are the reasons, prominent reason for swell in voltage. So the severity of the voltage swell during a fault condition is a function of fault location and system impedance and grounding, right? Fault location, system impedance and grounding. Suppose if the fault is occurring nearby this generating station, then it is considered to be the most severe fault, right? Most severe fault, because it is occurring near the generating stations, because no fault impedance is involved here. But on a contrary note, if the fault is occurring at farther end from the generating station, then this fault is considered to be the least severe. What is the reason? Reason is that a large amount of impedance is involved in this fault, so that's why it is a least severe, right? So this is the reason. It depends on fault location, system impedance and grounding as well, right? These three are the reason. Next is see here, the negative or zero sequence voltages and currents results from unbalanced load. Whenever there is a unbalanced load is there, then you can see the negative sequence voltages or currents and also zero sequence voltages and current. This will come in the system only when the load is unbalanced, right? So voltage unbalance is given by maximum deviation from so due to unbalanced loading, you will get negative sequence voltage and current and zero sequence voltage and current, right? Due to unbalanced loading, right? So what is voltage unbalance? It is maximum deviation from average voltage divided by average voltage. Percentage, if you want to calculate percentage, that means multiplied by 100, right? So this will give you the percentage voltage unbalance. How much voltage is unbalance you can determine from this, right? Now what are the sources? When a single phase, so what are the sources? Single phase loads on a three-phase circuit, it is less than 2%, right? Next is result of blown fuses in one phases of three-phase capacitive bank, right? Next is severe voltage unbalance, right, can result from single phasing condition. This is greater than 5%, right? So you see, this is you can say a rough sketch of voltage unbalance in a typical power system on a weekly basis from Monday to Saturday, right? On vertical axis I have plotted voltage unbalance in per unit, and on horizontal axis I have plotted the days: Monday, Tuesday, Wednesday, Thursday, Friday and Saturday, right? So you see, these are the fluctuations, right, representing your voltage unbalance. So this voltage unbalance, this is the voltage unbalance trend for a residential feeder, right, for a residential feeder. Now Voltage waveform distortion. What is a voltage waveform distortion? It is defined as a steady state deviation from an ideal sine wave of power frequency mainly. So waveform distortion, it is defined as a steady state deviation from an ideal sine wave of power frequency mainly characterized by spectral constraint of the deviation, right? The aim is to achieve the fundamental, right? So there are 5 types of distortion which you can find. Number 1, due to DC offset, distortion due to DC offset. Harmonics, it is again a kind of distortion. Interharmonics, again it's a distortion. Notching, it's a distortion. Noise, again it's a type of distortion, waveform distortion, right? So basically in rough terms I can call these 5 as a pollution. This is nothing but all these 5 are pollutions in the system, right? See here, harmonics, they are not said to be in use. The only use of harmonics you can see in heating, right? Remaining in all sort of applications, harmonics are not considered good for the system, right? See here, what are the DC offset? DC voltage, it is the presence of a DC voltage or current in an AC power system that is termed as DC offset, right? What are the harmonics? Harmonics are sinusoidal voltage or currents having frequencies that are integer multiple of the frequency at which supply systems is designed to operate, right? So that means multiple of 50 Hertz is known as harmonic. That means it can be 100 Hertz, right? 150 Hertz, okay, 200 Hertz, 250 Hertz, 300 Hertz, like this and so on. So multiple of fundamental, that means multiple of 50 Hertz is known as harmonics. Now IEEE standard 519 year 1992 provides guidelines for harmonics current and voltage distortion levels on distribution and transmission circuits. So periodically distorted waveforms can be decomposed into some of the fundamental frequencies and harmonics. Harmonic distortion originates in the non-linear characteristic of devices and loads on the power systems. Harmonic distortion levels are described by the complete harmonic spectrum with magnitudes and phase angles of each individual harmonic component, right? Harmonic distortion levels are described by the complete harmonic spectrum with magnitude and phase angles of each individual harmonic component, right? Now let me introduce next term, that is THD, stands for total harmonic distortion. What is THD? It's a total harmonic distortion. So THD is a measure of effective value of harmonic distortion, right? Effective value of harmonic distortion is total harmonic distortion. So THD is used to characterize both current and voltage waveforms. However, THD refers distortion of voltage waveforms mainly, right? Now see, this figure illustrates the waveform and harmonic spectrum for a typical adjustable speed drives, right? Input, right? So here on this axis you can plot current or you can plot voltage, right? Here I plotted for current, you can plot for voltage as well. So here you can see on horizontal axis this is a time in milliseconds. So minus 30, minus 20, minus 10, 0, plus 10, plus 20, plus 30, these are the values of this current, right? Now here at this point you can see there is these are the distortions, right, in the waveform. So total harmonic distortion, IEEE 519 sets the standards and limits on total harmonic distortion for utility side of the meter. Utility is responsible for the waveform distortion at the point of common coupling, right, between the utility and the end user. Now total harmonic distortion is a way to calculate voltage distortion effects of the injecting harmonic current onto the system, right? So basically we are talking about the pollution in the system. Harmonics is nothing but the pollution, right, which is undesired. Okay, so total harmonic distortion is a way to calculate voltage distortion effect of the injecting harmonic current on the system. Now total harmonic distortion is given as RMS of the harmonic content divided by RMS value of the fundamental. What is total harmonic distortion? THD is RMS of the harmonic content divided by RMS value of the fundamental component, right? So THD is a term used to describe the net deviation of non-linear waveform from ideal sinusoidal waveform, right? For current I have written, you can write it for voltage as well. So I suffix H stands for harmonic, under root, since it is root mean square value, that means I2 square plus I3 square plus I4 square plus I5 square plus I6 plus square plus I7 square and so on, right? I1 square is not there because I1 is for fundamental. So fundamental will not be counted as harmonic. So exclude fundamental, that is I1 square, exclude I1 square, and remaining all are harmonics. I2, I3, I4, I5, these are all harmonics. All are root mean square value, that's why these are an under root I2 square plus I3 square plus I4 square plus I5 square and so on, right? So THD is given as RMS of harmonic content divided by RMS value of the fundamental. That means calculate here from here IH by I1 is a fundamental. Percentage if you want to calculate, then multiply it by 100, right? So IH by I1 into 100 is THD. Or in terms of voltage, you can write VH by V1 into 100, that is total harmonic distortion, percentage total harmonic distortion for voltage waveform, right? Similar to current, you can write for voltage waveform as well, right? Now there is a small example. See here, find the total harmonic distortion of the voltage waveform with the following harmonic frequencies makeup. These are all given to you. Fundamental component of waveform V1 is given as 114 volts, third harmonic V3 is 4 volt, fifth harmonic V5 is 2 volts, seventh harmonic V7 1.5 volt, ninth harmonic V9 is 1 volt. Now RMS value of the harmonic VH is equal to under root V3 square plus V5 square plus V7 square plus V9 square. That means take the root mean square values of all these given harmonics VH, right? So VH comes out to be equal to 4.82. Just use your calculator to find out this value. So percentage total harmonic distortion, the voltage wave is given as VH by V1. V1 is fundamental, is given as 114. So 4.82 divided by 114. Percentage निकालना है तो 100 से multiply करिए. That means 100 percentage THD comes out to be equal to 4.23%. That is the answer. That means this much percent is the pollution. This much percent is the pollution, right, which is there in this waveform, voltage waveform for this particular system, right? 4.23% is the pollution, right? Now total demand distortion, let me introduce another term, TDD, total demand distortion. So IEEE 509 sets limitation TDD for the end user side of the meter. That means it is given as TDD is given as RMS of the harmonic current divided by RMS value of maximum demand of the load current. So percentage TDD if you want to calculate, then multiply it by 100. So that means it is expressed as a percentage of the rated load current. So TDD, that means total demand distortion, deals with the evaluating the current distortion caused by the harmonic current in the end user facilities, right? So TDD is given as harmonic content divided by demanded load current. So TDD is equal to under root summation of H is equal to 1 to infinity. H is harmonic, right? It can, a number can be go up to infinite, divided by demanded load current. Let us say it is IL. So here IL is RMS value of maximum demand load current. H is the harmonic order 1 2 3 4 etc. IH RMS load current at the harmonic order, right? Now next term is interharmonic. What is interharmonic? Voltages or currents having frequency component that are non-integer multiple of the fundamental frequencies, right? So sources of the integer harmonics, what are the sources? So voltage or current having frequency component which are non-integer multiple are known as interharmonics, right? The sources of interharmonics are waveform distortion, static frequency converters, cycloconverters, induction furnaces and arcing devices. So all these are the sources of interharmonics, right? What is a notch? Next term is a notch. Notching is a periodic voltage disturbance caused by the normal operation of the power electronic devices when current is commutated. That means when current is turned off. Commutation means turning off of the current. Turning off of the current is known as commutation. So notching is a periodic voltage disturbance caused by the normal operation of the power electronic devices when current is commutated from one phase to another, right? That means when current is switched off from one phase to another. So this is a simple graph, right? You can see here. So this shows the example of the voltage notching caused by three-phase converter, right? So here you can see this kind of curve, right? This shows the notch, right? Notch, which is basically periodic voltage disturbance caused by normal operation of power electronic devices. So thank you very much for your patience. Thank you very much for patience listening, right? Just revise this. Thank you, students. Thank you very much.